Hi everyone, in this video I'm going to cover both 7.2 and 7.3. Both lessons are quite short, so I'm merging them together, and they are about the normal distribution and its applications. Now, the normal distribution is probably the most common type of continuous probability distribution, and it's also important in statistics. So we are going to cover it in detail today and for the remainder of this chapter. Now, this type of probability distribution is very common in many things in real life. So the normal distribution, in real life, in everyday English, you also sometimes refer to it as the bell curve. The reason is it's because it's shaped like a bell. If we had frequency, our histogram, frequency or probability, the histogram should look a little something like this. Okay. Now, what this is like is that there is a mean that is also, in a sense, the median and mode. And it is symmetrical, and the thing is, there are many things in real life that can be modeled around this. Examples include people's height and weight. If you took a large group of people who had similar characteristics, like same gender, around the same age, you should get heights where it is centered around a mean. Okay, and the further away you go from the mean, the probability of a person having that height becomes lower and lower. Manufacturing, when we make things, for example, if we make things to a certain size, we can usually get it to making it that size. But there's also probability that it can be slightly bigger or smaller. But the probability that it will be very off, a lot smaller, a lot bigger, gets smaller and smaller. Test scores. If you took a large group of students and had them write a test, it would be centered around a mean. And the further away you go from the mean, the less likely that that student will get a test. So there can be a lot of students who do quite well on the test, and some students who do a bit better or a bit worse, but a lot fewer students who do much better or much worse. Okay, so those are examples of things that can be modeled by a normal distribution. Now, depending on the standard deviation, the normal distribution can look flatter or pointier, but the probabilities remain the same. As long as you know how many standard deviations from the mean an interval of data values are, the probabilities are always the same for a normal distribution. So the graph, the bell curve shape, can look narrow like this. This is when we have a small standard deviation. If we have a large standard deviation, then it looks flatter. Now, with a small standard deviation and large standard deviation, the probabilities, depending on the number of standard deviations from the mean, are the same. So, for example, if this was one standard deviation above the mean here, and same goes for here, this area right here is equal to this area right here. So the probabilities are the same for the same number of standard deviations from the mean. All right, let's look at an example at things that might be modeled by a normal distribution first. Then we're going to look at how to calculate probabilities for things that can be modeled by a normal distribution. So let's look at a simple example first from 7.2, example 1. A men's clothing store kept records of the waist sizes of a sample of their customers measured to the nearest quarter of an inch. The table shows the relative frequencies, so that's just the total frequency divided by the total frequency, the frequency of the interval divided by total frequency. All right, so here we can make a histogram of the data. All right, so here we have frequency or relative frequency, and our data value x is the wave size, or random variable rather. Okay, so we can have a little break on the x-axis, and let's start with 26. Maybe every 2 squares can represent 1 if we have enough space, or maybe not. 28, 30, 32, 36, 38, 40, 42. And for our relative frequency, that goes up to 0.3. So let's say every 5 squares represent 0.1. So 0.025, something like this, 0.175, 0.295, that's almost up here, 0.3, 0.16, and lastly 0.045. All right, so we see it's not perfect, but it is kind of like a normal distribution. If we were to make a frequency histogram, the frequency histogram would look something like this, right? Okay, so I just noticed I made a slight mistake for my intervals. 32, there should be 34, 36, 38, 40, and here we have 42. Okay, so we can see it kind of looks like a bell curve, close enough. So we can model it using a normal distribution, or we can assume that this random variable is normally distributed. What is the rule for how standard deviations work with the normal distribution? Now, with the change in standard deviation, the probability for the number of standard deviations from the mean remains the same. Okay, what does this mean? It doesn't matter what the standard deviation is, okay, or the mean is. Then if we know how many standard deviations from the mean, remember that is calculated from the z-score. If we want to calculate how many standard deviations from the mean something is, the probability always remains the same. Right? So this example of normal distribution curve, this graph right here, gives you some general rules. 68.2% of data values are within one standard deviation of the mean. So from a z-score of -1 to 1, that covers 68.2% of the data values. Within 2 standard deviations of the mean, you cover 95.4% of the data values. All right, that means 95.4% of data values are less than 2 standard deviations greater than the mean, or more than 2 standard deviations less than the mean. Once you get to 3 standard deviations, you pretty much cover all the data values. You cover 99.7% of the data values. It is very unlikely that any data value will be more than 3 standard deviations within the mean, either greater or less. And the thing of the normal distribution curve is it actually goes on forever, from both left and right. But the probabilities get very, very, very small. So we don't need to really worry about finding probabilities for outcomes that are, say, 4, 5, or 6 standard deviations from the mean. Okay, so if we were given the number of standard deviations from the mean, we need to solve for a probability, and we need to solve for probability normal distribution. We only need to look at the z-score table, or what's sometimes called the normal distribution table. This is a table that gives you the probabilities that you will get a particular z-score or less for that. So when you're given a data value, you have to get the mean and the standard deviation first. And then you can calculate the probabilities that it is less than that data value, greater than that data value, or between that data value and another. I'm going to make another video, or there should be another video later on, where I will show you how to use the z-score table. All right, let's look at 7.2 example 2. 40 airplanes participated in a spot landing contest at the aerodrome. The landing zone was 30 meters long, with the target line at the 15-meter mark, so right in the middle. The table shows the touchdown position of each airplane along the landing zone. The data in the table are expected to follow normal distribution. So use graphing software to create a histogram of the data. Verify that data can be modeled by normal distribution. So I already did that with Google Sheets. I got something like this, okay, and I made a frequency polygon as well. We can see it's kind of bell-shaped, not perfect, okay, but close enough. So we can see that can be modeled by normal distribution. Modeled meaning giving us approximate answers, not exact, but close enough. Okay, so it looks like a bell curve, so we can model data using normal distribution. Determine the mean and standard deviation of the spot landing data. Okay, so I did those calculations myself. I added up all the data values, divided by the number of data values. I got 14.63. The standard deviation is 3.22. I should say this should probably be S, since we're looking at a sample. Or is it a population? In this case, either one is fine. For me, we're not quite clear. I'll try to be clear if I ask a quiz or test question. What is the z-score for a pilot who lands her plane at a position 18.3 meters? Remember the z-score formula. Okay, we get our data value minus the mean divided by the standard deviation. So it's 18.3, that's our data value given, minus 14.63 all over 3.22. So when we have our z-score, that can give us the probability. The z-score table will give us just looking up the z-score table will give us this probability, 18.3 meters or less. The number that you get on the z-score table is the probability that it's 18.3 meters or less. Looking up the z-score table, okay, it's a z-score of 1.4. You have to look up 1.14, and you'll see that you get a probability of 0.8729, more than 18.3 meters. Okay, so like I mentioned, the z-score table, okay, let's say this is 1.14. The z-score gives you the probability of that or less, right? So it's going to give you all of this right here. Now, if I want more than 18.3 meters, then 18.3 meters corresponds with a z-score of 1.4. I'm trying to get this area right here, right? And what do we learn about the area of a histogram? A probability histogram, it adds up to 1. So more than 18.3 meters, we just get the number from the z-score table. Okay, we get 1 minus the number from the z-score table. So 1 minus 0.8729, which is 0.1271. All right, last one, between 12.2 and 18.3 meters. Again, looking at the normal distribution curve and how the z-score table works, All right, we know 1.14 right there. The z-score table gives us all of this area right here. 12.2 meters, that's going to be a z-score that's less than 0, right? Because the mean is 14.63. So whatever the z-score we get for that, okay, is the probability of all of this area right here. Okay, if I want to find the probability between 12.2 and 18.3 meters is therefore this part of the normal distribution curve, right? So I can get that by getting the red area, which is the probability from the z-score 1.4, minus the blue area, which is the probability from the z-score of whatever 12.2 meters is. So I gotta subtract. Okay, first I get the z-score for 12.2 meters, which is negative 0.75. So the probability between would just be the probability from the z-score 1.4 minus the probability from the z-score of negative 0.75, which is 0.2266 if you look up the z-score table. That gives me 0.6463. So there's about a 64.60% chance that the pilot will land between 12.2 and 18.3 meters. Okay, let's look at 7.3 example 1 now. So here we're just going to do some more practice. These don't really require the z-score table because we're looking at 1 and 2 standard deviations, which you guys should already know from the graph I showed you earlier. Okay, so suppose the scores for a nationwide math test follow a standard normal distribution with a mean of 30 and a standard deviation of 12. What is the probability that a large sample lies within one standard deviation of the mean? So we already, 2 standard deviations, we already saw from the graph what that is. Okay, remember 68.2% are within 1 standard deviation, 95.4 are within 2 standard deviations. Okay. B, does the answer in A depend on the mean and standard deviation? If the standard deviation changed, is the probability that a large sample lies within 1 or 2 standard deviations, is that going to change? Or if the mean changes? As I mentioned earlier, the answer is no. Okay, as long as we know the number of standard deviations from the mean, which is the z-score, then we can find a probability. All right. So the answers would not change if the mean and standard deviation changed. Okay, so that pretty much is our introduction to the normal distribution. Make sure you know how to use the z-score table, and make sure you understand the basic concepts of how the normal distribution works. Here are some practice questions. I recommend you give them a try before you do the assigned textbook questions. And that's it for today's lesson.